So blockchain security relies on miner incentives. Past studies simplistically assumed constant rewards, but in Wellman, we introduce and solve a refined model with varying rewards. Traditional solving methods fall short. Instead, we use deep reinforcement learning with novel variance reduction techniques. Our findings reveal that reward variability undermines blockchain security, suggesting a future deterioration of Bitcoin security. So blockchain protocols should distribute rewards to their miners in proportion to how much computational power they invest. However, large enough miners can deviate from the protocol to gain an additional share of the rewards. And the minimum miner size required to do so, what we see in the vertical dashed line, is called the security threshold. So as long as all miners are smaller than the threshold, everyone is properly incentivized and we get a Nash equilibrium. But if a single miner is larger than the threshold, there's enough computational power, the miner can deviate, perform selfish mining, and the security properties of the blockchain no longer hold. Okay, so a few words about blockchain, some background. So a blockchain is a chain of blocks. Each block points to the previous block. And each block also contains transactions. And in our work, we focus on Bitcoin-like protocols, which operate using proof of work, meaning that a miner has to expend computational power to solve a cryptographic puzzle in order to create a valid block. This is a probabilistic process. So the more computational power a miner expends, the higher chance they get to create a valid block. And to compensate for the computational power, miners are rewarded for every block they create, and also for every transaction they include in the blockchain. Block rewards are constant and basically tokens created by the protocol to be given to the miner. But the transaction fees values are set by the issuers of the transactions. So this is a dynamic reward system. There are more transaction issuers want to pay. Sorry. If transaction issuers want their blocks to be included, they have to pay enough. Okay. And the security of Bitcoin relies on the longest chain rule. In the case, there are two conflicting blocks, two blocks that point to the same block. The rule is you have to follow the longest chain. Okay? And the idea is that this, as long as an honest majority follows this chain, it should go the fastest. And this makes it harder for an alternative chain to be created. Okay, and I'm going to go for a simple example of selfish mining. Why should it be profitable? We're going to go for a case which showcases this. And this is a probabilistic process, so there are many probabilities behind, but we're going to look for a very specific trajectory. And we're going to take a look at it from two viewpoints, the viewpoint of the honest network on the left and the viewpoint of the selfish miner. So let's say there's a block everyone knows about and tries to mine on. If the selfish miner manages to create a block, he can keep it a secret and not reveal it to everyone else. Okay? And then the selfish miner can mine an additional block on the block he created and keep both blocks a secret. Okay? And now, if an honest miner finds a block, he's not aware of blocks B and C. So his block points to block A. And in this case, the selfish miner can reveal both blocks to everyone else, causing them to now follow the longest chain. So block D is essentially discarded also by honest miners. And by wasting the computational power of other participants, the selfish miner increases his relative reward. Okay. So let's talk a bit about related work and how does WeRLman contribute. So as I said before, the security threshold was thought to be 50% from the start because the intuition was that as long as we have an honest majority working on the longest chain, we should be okay. But that's not the case, and the Eyal showed a selfish mining strategy which achieves higher than a selfish miner can use to gain more rewards. And the selfish miner needs at least 25% of the computational power resources in the system. And this means that the threshold is 25% at most. We still don't know if there's another strategy which can net more reward, and maybe an even smaller miner can use it to profit. If you really want to find the security threshold, the minimum miner size required to deviate, you have to find the optimal strategy. Okay, you have to look at it at the mining process from the viewpoint of a rational miner trying to maximize revenue. And this can be done inside a Markov decision process, or an MDP. And it was done before by Sapir-Stein et al., and they actually found that the security threshold is 25% if you use the optimal strategy. And their model only considered the constant block rewards made by Bitcoin and neglects transaction fees. So 2 subsequent works try to understand what happens if you do consider transaction fees. But due to complexity, they focused only on transaction fees and neglected block rewards. And they found that the security threshold is non-existent. In this case, you can't really rely on transaction fees only. However, this model only applies about 100 years into the future. And this raises the question of what happens today. Today in Bitcoin, we have both block rewards and transaction fees. And that's the answer we're trying to answer with, the question we're trying to answer with WeRLman. Okay. So what do we do exactly in Wellman? So previous analysis done by Sapir-Stein used the state which looks something like this. You have 2 competing chains, and all blocks are worth the same. So you only need to remember the length of the chains. This is like a miner sailing in smooth waters. All blocks are worth the same. But in practice, some blocks are worth significantly more than others. And we model this in WeRLman by the notion of whale transactions. Occasional transactions which are worth significantly more than others. And now our model allows for 2 types of block. An empty block, which gives 1 unit of reward, and a block containing a whale transactions, which give 1 plus f, where f is some parameter of how much a whale transaction is worth. Okay. And now our state looks something like this. We have to keep track of the locations of the transactions. This causes the state space to be much larger and more complex. And this has to be captured by 2 Boolean vectors instead of 2 scalars. And this explosion of the state space leads to orders of magnitude more states, and now we cannot use previous solution methods. Instead of using dynamic programming, as in by Sapir-Stein et al., we have to use deep reinforcement learning. Okay. I'll explain shortly about deep reinforcement learning in 2 slides. The main idea is that you train a neural network so that when you give it a state, it will give you back the optimal actions to choose. Okay, so for example, in this state, you have 2 blocks competing with one. The neural network tells you to publish the private chain. And this has seen great success in the past in Atari games and Chinese Go by finding patterns within the state in order to be able to express the optimal action. Okay, and in Wellman, we also use variance reduction techniques. This is very important because calculating the security threshold is very sensitive. The security threshold depends on very slight deviations which give a very minor advantage to the miner. And therefore, we needed Wellman to be highly accurate. And to do that, we employed a long look ahead with Monte Carlo research. And in addition, we used 2 novel variance reduction techniques which are not used in conventional reinforcement learning. One, we utilize the knowledge of transition probabilities. Usually in reinforcement learning, this is not done. You assume you do not know the transition probabilities, but using them, if you do know them, gives much lower variance in the training process. In addition, we use the recurrent nature of the mining process to automatically scale the neural network. We essentially use the domain knowledge we have in our specific problem to scale the neural network appropriately. And combining all of these techniques results in a much better training process. Okay, if you consider the training epochs we have in WeRLman and compare it to a baseline RL method, you get much higher revenue. And we also evaluated WeRLman on a toy model where we constrained the number of states so we could solve the model optimally. And in this case, we saw that in all cases we considered of different minor sizes, WeRLman finds the optimal strategy. We then try to find the security threshold using the full model with the entire state space. So if you take a look at what happens for different minor sizes, every single point is a single run of Wellman. Okay, so we feed it the minor size, and it finds the best strategy. And we use that to search for the security threshold. We try to look for the minimum minor size for which Wellman finds a strategy better than honest mining. That's the vertical line. Okay, and if we do the previous process many times for different parameters of f, we can find the security threshold as a function of the model parameters, and specifically for the value f, we see that increasing f results in a dramatic decrease of the security threshold. And f corresponds to the reward variability. It is the ratio between the high rewards and the low rewards. So we conclude that reward variability hurts blockchain security. And this has grave implications on Bitcoin. We use on-chain data to estimate values of f using some heuristic, which I'll skip now. And we find that because of the block rewards in Bitcoin is scheduled to have every 4 years, this is by Bitcoin's design, the inherent variability of the transaction fees will become more dominant in the future. And as more halving events occur, the lower the security threshold is going to be. For example, in 30 years, it's going to be less than 13%, which is significantly lower than minor sizes today. Okay, so thank you very much. I presented WeRLman, an open source, accurate DeepRL method for analyzing incentives in blockchains. You can scan the QR to get to our code. And I also encourage you all to come to my workshop talk where we expand the model to also allow a selfish miner to bribe other miners and see that it has even more negative impact on the security.
Okay, thank you. Very nice. Questions? Anyone, local or remote? Yeah.
Hello, Ruomu from National University of Singapore. So I want to ask, what is the significance of the security threshold? So my understanding is that if, let's say, the security threshold is very low, then anyone who have mining power more than the threshold will turn to selfish mining, right? So what exactly is security impact of that? So let's say if many people choose to do selfish mining, so what?
Basically, when one miner chooses to perform selfish mining, it changes the incentives of other miners, which will be more likely to also use selfish mining. And it also makes it easier for others to attack the system. Miners will not cooperate, causing the chains to grow more slowly. So performing double spending or 51% attack will be even easier if one miner doesn't follow the protocol. Basically, it creates a cascade where this entire security falls apart.
So like this cascade will make like tax more easier, or okay?
Yes.
So is there any like quantitative result on like how easier or no?
I think there is a paper which analyzes what happens when you have multiple selfish miners. We didn't look into that, but Squirrel did that and showed that it's not an Nash equilibrium. And
okay, thanks.
Good. Yeah, Joe.
Hey, great talk. Have you thought about different proposals for reward smoothing and how that might impact this? Like this seems to suggest that's something maybe people should get more serious about.
I thought about it slightly, but there are problems with remote smoothing from their design. So I don't really know if it will change the impact of the work, because these can be avoided by using black markets for transaction, for example. So we didn't really think about that.
Okay, thanks.
Thank you.
Yeah, one more quick question, then we'll have to move on.
Yeah, the values you gave for the security threshold, I think you said 0.13 and maybe 0.2 at some point. What was the gamma or the rushing factor for those? And what did you find when you varied that gamma from like arbitrarily high to arbitrarily low? What did you find there?
Yes, basically when you change gamma to be very low, you get that the threshold increases, and gamma equals 1 means no threshold. In all the values I used, we used gamma equal half just to get a sense of something. But we have that in the paper, a graph which shows gamma, the impact of gamma.
Okay, thank you again.